This is a video of light traveling through a bottle, not a simulation, not an animation. Actual light moving at 300 million meters per second, frozen in time by a camera. You can see the wavefront spreading beneath the glass. You can watch photons bounce off the cap. For all of human history, light was instantaneous. We never saw it move. And now, for the first time, we can. But here's what troubles me. If something this fundamental was invisible to us for millennia, what else are we missing? What else exists in the spaces between our heartbeats, in the silence between our thoughts, that we're moving too fast to see? We live our lives at human speed. We evolved that way. Our ancestors on the African savanna needed to react quickly to survive. A rustle in the grass meant danger. Hesitation meant death. So natural selection gave us eyes that blink every 150 milliseconds, neurons that fire every 10 milliseconds, a brain optimized for rapid response. We are biological machines built for speed, built for survival. And we're very good at it. We survived, we thrived, we inherited the earth. But there was a cost to that speed. In our evolutionary rush to react, to flee, to endure, we became blind to almost everything that exists. We see only the thinnest slice of reality, the narrow band of frequencies and timescales that kept our ancestors alive. Everything else, all the intricate machinery of the universe operating at speeds too fast or too slow for our biology to detect, simply vanished from our awareness. We didn't even know it was there. For most of human history, we assumed that what we could see was all there was to see. The sun rose instantaneously. Objects fell in continuous motion. Matter was solid and still. We built entire philosophies on these assumptions. We constructed worldviews around them. And we were wrong, not slightly wrong, profoundly, fundamentally wrong. We just didn't know it yet because we'd never slowed down enough to look. In 1930, there was a man named Harold Edgerton. He was an electrical engineer at MIT working on a problem with electric motors. These motors powered factories and mills, the industrial backbone of America, but they had a flaw. They were sensitive to power surges. A lightning strike could make them behave unpredictably, dangerously. Edgerton wanted to understand why, but he had a problem. The motor spun too fast for the human eye to see. Cameras at the time were useless. Their exposure times were too slow. Any photograph of a running motor came out as an indistinct blur. But one day, Edgerton noticed something. Every time he triggered a power surge in his lab equipment, there was a bright flash of light, and in that brief flash, the motor appeared to freeze. The spinning gears stood perfectly still, as if time itself had stopped. It gave him an idea. What if he could create these flashes reliably? What if he could illuminate the motor with a light so brief, so intense, that it would capture a single frozen instant? He built what we now call a strobe. A device that could produce flashes of light lasting only 10 microseconds, 10 millionths of a second. He would turn off all the lights in the room, open the camera shutter, and wait in darkness. No light, no image. Then, at the precise moment he wanted to capture, the strobe would fire. One brilliant flash. And the camera would record that single instant with perfect clarity. Edgerton wasn't the first to invent a strobe. Others had made similar devices, but Edgerton had something unique. He had an eye for beauty. He saw possibilities beyond motors and machinery. His wife once complained after seeing his 300th photograph of a synchronous motor. She said, "Harold, can't you take a picture of something a little more interesting?" And so he did. He photographed a tennis ball compressed against a racket, its surface deformed like a pancake. He photographed hummingbirds frozen in mid-flight, their wings spread in perfect geometric precision. He photographed a drop of milk hitting a plate, creating a liquid crown of impossible delicacy, droplets suspended in a corona that existed for only a few milliseconds before collapsing back into chaos. These images appeared in Life magazine, in National Geographic. They were seen by millions, and they changed something fundamental in how we understood the world. Because here's what Edgerton revealed. The tennis ball had always compressed that way. The hummingbird's wings had always moved in that pattern. The milk drop had always created that crown. These phenomena had existed for as long as tennis balls and hummingbirds and falling liquids had existed, but we had never seen them. We were moving too fast. We assumed we knew what we were looking at. We thought a tennis ball simply hit a racket. We thought a hummingbird's wings were a blur. We thought milk just splashed. We're wrong, and we didn't even know we were wrong until someone slowed down enough to show us. This is what I call the first quiet realization. It's not about the technology, it's about humility, it's the understanding that the world we think we see is not the world as it actually is. It's merely the world as our biology allows us to perceive it. When we slow down, when we look more carefully, we discover we've been missing almost everything. Think about what this means. How many other things do we assume we understand simply because we've never looked closely enough? How many phenomena exist in the gaps between our perceptions, operating at timescales our nervous system cannot detect? The answer, I suspect, is almost everything. After Edgerton, others pushed further. They built cameras that could capture thousands of frames per second, then hundreds of thousands. The technology improved, the images became sharper, but there was always a trade-off. The faster you wanted to capture motion, the fewer pixels you could record. You could have high resolution or high speed, but not both. Physics imposed a fundamental limit. To read data off a camera sensor takes time. To go faster, you have to sacrifice detail. Unless you do something clever. At places like MIT and the University of Toronto, scientists realized something. If the scene you're photographing is perfectly repeatable, if the same event happens the same way every time, then you don't need to capture the whole scene at once. You can capture it one pixel at a time. You point your camera at the top left corner, record what happens there, then move slightly and record the next pixel. You do this hundreds of times, thousands of times, building up a complete image pixel by pixel, moment by moment. It sounds tedious. It is tedious, but it lets you do something remarkable. You can push the frame rate not to thousands per second, not to millions, but to 1 trillion frames per second. 1 trillion. At that speed, each frame lasts only 1 picosecond, 1 trillionth of a second. In that time, light itself travels only 3/10 of a millimeter. And that means you can watch light move. Let me say that again because I want you to understand how profound this is. You can watch light move. Light, the thing we have always known as instantaneous, the universal speed limit, the cosmic constant becomes visible. You see it crawl across a room. You watch it bounce off surfaces. You witness it as a thing that has speed, that has motion, that takes time. This is the second quiet realization. There is no now. There never was. Every photon you see left its source moments ago. When you look at the sun, you're seeing it as it was 8 minutes in the past, the time it took for light to cross 150 million kilometers of space. When you look at the nearest star, you're seeing it as it was 4 years ago. When you look at distant galaxies, you're seeing them as they were billions of years before humans even existed. But it's not just distant objects. Even the person sitting across from you is a ghost. You're seeing them as they were nanoseconds ago, the time it took for photons to bounce off their face and reach your eyes. There is no such thing as seeing something now. By the time the light reaches you, by the time your neurons process that information, by the time you become conscious of the perception, the moment has already vanished into the past. We live in a universe of echoes. We always have. We just never slowed down enough to notice. When you photograph light at 1 trillion frames per second, you're not just seeing faster, you're crossing a threshold. You're leaving the world of human intuition and entering a realm where our evolutionary instincts have no power. A picosecond is already beyond comprehension, but we can go slower still. An attosecond, 1 quintillionth of a second to understand the scale. Imagine this, 1 attosecond is to 1 second what 1 second is to the entire age of the universe. 13.8 billion years, the entire history of cosmic evolution from the Big Bang to this moment, compressed into a single heartbeat. That's how far removed an attosecond is from human experience. And yet, there are cameras that can see at this scale. They exist at places like the Stanford Linear Accelerator, a perfectly straight tunnel 3 kilometers long buried beneath the California Earth. Inside that tunnel, electrons are accelerated to more than 99.9999992% the speed of light. They race through devices called undulators, arrays of magnets that force the electrons to wiggle. And when electrons wiggle at near light speed, they emit X-rays. Incredibly bright, incredibly brief pulses of X-rays lasting only a few hundred attoseconds. These X-ray pulses are used to photograph something even more elusive than moving light. They photograph electron clouds, the quantum probability distributions that orbit atomic nuclei, the ghostly entities that create all chemistry, all molecular bonds, all the matter we're made of. Here's how it works. You take a molecule, any molecule, and you hit it with a laser pulse. That laser excites the molecule, kicks it into a higher energy state, starts some kind of chemical process. Then, After a carefully controlled delay measured in femtoseconds, you hit it with the X-ray pulse. That X-ray ejects an electron from the molecule's core. And by measuring the energy of that ejected electron, you can infer what the electron cloud looked like at that precise instant in time. Then you take another molecule identical to the first and repeat the experiment. Same laser pulse, same chemical reaction. But this time you increase the delay slightly. A few hundred attoseconds later, you get another snapshot, another frame. You keep doing this, increasing the delay each time. And you build up a molecular movie, a film of electron clouds shifting and flowing around atoms as chemical bonds break and form. The scientists who do this work have created simulations of what they expect to see. The equations of quantum mechanics predict how electrons should behave when a molecule is excited. For the first few femtoseconds, their predictions match the measurements perfectly. Theory and experiment agree. The universe behaves exactly as we calculated it should. And then something happens around 5 to 10 femtoseconds. The predictions start to diverge from the measurements. The electrons do something unexpected. Something the equations didn't predict, something we don't fully understand. This is the third quiet realization, and it's the most important one. When a physicist shows me these results, when I see that moment where theory and measurement part ways, I don't feel disappointment. I feel something else, something deeper, because this is not failure. This is science at its most honest, its most beautiful. We thought we understood electrons. We wrote equations. We made predictions. We were confident, and we were wrong. That wrongness, that gap between what we expected and what we observed is not a problem to be solved. It's a gift. It's the universe telling us quietly, patiently, that there's more to learn, that our equations, elegant as they are incomplete. That reality is stranger, richer, more complex than we imagine. I once asked a physicist a simple question: do electrons exist? I expected a simple answer. Yes, of course they exist. We've built entire technologies around them. But instead, he paused, he looked at me carefully, and he said, how truthful do you want me to be? Because the truth is we don't know. Not in the way we know a chair exists. We can't see electrons, not even with the most powerful microscopes ever built. We can only write mathematical expressions that predict what they'll do. We can describe their properties. We can measure their effects. But we cannot picture them. We cannot visualize them in any way that makes intuitive sense. They are sometimes particles. They are sometimes waves. They are always something we cannot quite grasp. And that, I think, is the deepest lesson of slowing down. The slower we look, the stranger things become. The hummingbird's blur becomes visible wings. Fine, we can understand that. Instant light becomes visible motion. Harder, but we can accept it. But electrons refuse to be anything we can comfortably comprehend. They exist, if exist is even the right word, in a realm beyond visualization, beyond intuition, beyond the comfortable categories our minds evolved to work with. So what happens when you keep slowing down? You don't find answers, you find layers. Each time you slow down, each time you look more carefully, you discover that what you thought was reality was merely appearance, an illusion created by the speed at which you were moving. The solid table is mostly empty space. The empty space is filled with quantum fields. The quantum fields are excitations in something we call the vacuum, which isn't really empty at all. Every answer reveals deeper questions. Every question opens onto mysteries we haven't even learned to ask yet. And somewhere at the bottom of all the slowing down, there's a truth we cannot yet reach. Maybe we never will. The universe doesn't owe us understanding. It doesn't owe us intuition. It exists on its own terms, at scales we barely comprehend, following rules we're only beginning to glimpse. All we can do is slow down, look closer, and accept with quiet humility that we are very small, very recent creatures trying to understand something vast and ancient and profoundly strange. For most of history, we moved at human speed and assumed that was enough. We saw the sun rise and thought we understood light. We saw objects fall and thought we understood gravity. We felt solid matter and thought we understood atoms. But when we slowed down, really slowed down, we discovered we'd been wrong about almost everything. That wrongness, that humility, that quiet realization that the universe is stranger and more beautiful than we imagine is not a defeat. It's the beginning of wisdom. Because once you accept that you've been missing most of reality, once you understand that your perceptions are not truth, but merely useful approximations, you become open to wonder. You become capable of learning. You become, in the deepest sense, scientific. I think about Harold Edgerton standing in a darkened room with a strobe, capturing images of events that lasted only microseconds. I think about the scientists at Stanford accelerating electrons to near light speed, photographing quantum clouds that exist for attoseconds. And I realize they're all doing the same thing. They're slowing down. They're looking more carefully. They're asking the universe to reveal itself more honestly. And the universe in its patience obliges. It shows us that light moves, that electrons dance, that solid matter is mostly emptiness, that time is not what we thought it was, that now is an illusion, that we live in a cosmos far stranger than our ancestors could have dreamed. But it only shows us this when we slow down enough to see it. So perhaps the question is not, what happened when you keep slowing down? Perhaps the real question is this. What else are we missing because we're moving too fast to see? What other realities exist in the spaces between our perceptions? What other universes operate at timescales our biology cannot detect? I don't know the answer. Nobody does. But I know this. Every time we've slowed down, every time we've looked more carefully, we found something astonishing, something that changed how we understood everything. And I deeply suspect that we've only just begun. That there are layers upon layers of reality still hidden from us, waiting for someone curious enough, patient enough, humble enough to slow down and look. The universe is under no obligation to make sense to us, but it is, in my experience, endlessly willing to reveal itself to those who approach it with patience and wonder. All it asks is that we slow down, that we look carefully, that we accept we might be wrong about everything we think we know. And in that slowing down, in that careful looking, in that acceptance of our own ignorance, we find something more valuable than certainty. We find the quiet realization that we are part of something impossibly vast, impossibly strange, impossibly beautiful. And that realization, that moment of cosmic humility, is perhaps the most human thing we can experience. Because in the end, we are the universe looking at itself. We are matter that has become conscious atoms that have learned to wonder. And when we slow down, when we truly see what we've been missing, we're not just observing reality, we're participating in it. We're becoming worthy of the cosmos that made us. That's what happens when you keep slowing down. You don't just see more, you become more. You join the ancient conversation between curiosity and mystery, between the known and the unknowable, between the human need for understanding and the universe's infinite complexity. And in that conversation, in that endless dialogue between our questions and reality's answers, we find our deepest purpose. We find wonder.